Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Inside a steel-making furnace, temperatures can easily exceed 1,600 degrees Celsius, a level of heat that instantly liquefies ordinary structural steel. Yet only a few hundred millimeters away, the furnace exterior remains cool enough to touch safely without structural failure. What prevents this massive thermal energy from destroying the vessel containing it? The answer is not a single supermaterial, but a multi-layered ceramic barrier known as a refractory lining. Heat alone is only one of many destructive forces acting on this barrier. The ceramic lining must simultaneously survive turbulent molten metal, corrosive chemical slag, physical abrasion, and violent thermal cycling. Today, we go deep inside a refractory production plant to examine the exact science behind these industrial shields. We will trace the entire manufacturing life cycle, from raw mineral extraction to high-tonnage forming, precision firing, and furnace relining. A refractory is an engineered, non-metallic material capable of maintaining structural integrity and chemical inertness under extreme heat. In industrial applications, refractoriness alone is never enough to ensure a long campaign life. The hot face layer directly contacts flame, corrosive slag, and liquid metal, demanding high density and exceptional chemical resistance. Directly behind the hot face sits a safety lining engineered to catch liquid metal leaks before they contact the steel shell. The outermost layer consists of specialized insulation designed solely to trap thermal energy and minimize shell temperatures. This layout creates a classic metallurgical trade-off between thermal efficiency and mechanical durability. Acidic process conditions require silica-rich or alumino-silicate refractories to avoid aggressive chemical dissolution. Basic steelmaking conditions dominated by lime-rich slag require magnesia or Doloma refractories to prevent rapid chemical fluxing. High-alumina, silicon carbide, zircon, and carbon-bearing compositions are selected when abrasive wear, thermal shock, or redox reactions intensify. Refractory manufacturing begins with mineral geology, where chemical purity directly dictates maximum operating limits. Fireclay and kaolinite supply the baseline alumina and silica required for standard industrial bricks. Bauxite, andalusite, kyanite, sillimanite, and synthetic alumina are mined and processed to manufacture high-performance alumina linings. Engineers incorporate synthetic graphite, silicon carbide, zirconium silicate, and synthetic spinel to impart specialized thermal and mechanical properties. Raw minerals cannot be used in their natural state because thermal decomposition would cause catastrophic shrinkage during furnace operation. To prevent this, minerals undergo high-temperature calcination to drive off crystalline moisture, carbon dioxide, and volatile organic matter. Tabular alumina, for instance, is sintered at temperatures exceeding 1,800 degrees Celsius to recrystallize alpha alumina into massive, dense grains. Magnesite is dead-burned in shaft kilns or electrofused above 2,800 degrees Celsius to eliminate lattice reactivity. Every incoming mineral batch undergoes strict spectroscopic verification for trace oxides and crystalline phase purity. Once calcined, dense mineral aggregates enter heavy industrial jaw crushers, cone crushers, and impact mills. The crushed aggregates are continuously fed through multi-deck vibrating screens to separate distinct particle size distributions. The screen decks classify material into coarse aggregate, intermediate chips, fine sands, and microground flours. Refractory performance depends heavily on the mathematics of continuous particle size distribution. If you pack a volume with only coarse particles, large interstitial voids remain between each contact point. Automated batching plants weigh each particle fraction with industrial load cells controlled by computerized dosing algorithms. A single recipe often balances 6 to 10 separate particle classifications to achieve target bulk density and workability. Conventional fired bricks rely on high-energy mechanical pressing, followed by high-temperature ceramic vitrification. Graded mineral aggregates and reactive matrix powders are loaded into high-intensity pan mixers with precise liquid binder additions. Temporary organic binders such as lignosulfonates or dextrin give the pressed powder enough green strength to survive material handling. The homogenized mix discharges into massive mechanical, hydraulic, or friction presses, exerting pressures exceeding 1,500 kilograms per square centimeter. This immense compressive force pushes air out of the particle matrix and brings adjacent grains into intimate mechanical contact. The pressed green bricks are stacked onto kiln cars and routed through continuous counterflow drying tunnels. Thermal energy activates solid-state diffusion, driving, sintering, grain boundary migration, and secondary mineral formation like mullite or spinel. The resulting ceramic bond locks aggregate grains into a rigid, monolithic crystal network capable of bearing structural loads at white-hot temperatures. Certain industrial environments degrade ceramic-bonded bricks, necessitating non-fired, chemically bonded alternatives. Magnesia-carbon bricks, the backbone of modern secondary metallurgy, combine high-purity, dead-burned or fused magnesia with natural flake graphite. Because graphite rapidly oxidizes at elevated temperatures, these bricks cannot be fired in conventional oxygen-rich kilns. Instead, the magnesia grains and graphite flakes are blended with thermosetting phenolic resins and metallic antioxidant powders like aluminum or silicon. Tempering polymerizes the synthetic resin, forming an isotropic, highly cross-linked carbon polymer backbone. During furnace startup, the resin carbonizes into a permanent carbon bond that holds the magnesia structure intact. Modern metallurgy increasingly relies on unshaped or monolithic refractories that form seamless monolithic structures directly inside the vessel. Conventional castables rely on calcium aluminate cement, but modern engineering favors low cement and ultra-low cement castable technologies. These advanced formulations use submicron silica fume and reactive alumina to reduce the cement content to less than 2%. For the most punishing thermal environments, such as glass melting furnaces, manufacturers turn to fused cast refractory technology. Raw zircon sand, high-purity alumina, and pure quartz are blended to form an alumina-zirconia-silica composite, commonly known as AZS. The raw batch is charged directly into an electric arc furnace and melted completely into a homogeneous liquid at 2000 degrees Celsius. The incandescent liquid is cast into precision graphite or bonded sand molds to form massive solid blocks. These blocks undergo an intensely controlled multi-week annealing process inside insulated cooling bins. Controlled cooling prevents thermal shock fractures as the internal zirconia crystals undergo phase transformations during solidification. The diverse operating conditions across metallurgical processes demand specific, tailored refractory chemistries. Fireclay refractories with 30 to 45% alumina remain the cost-effective standard for low-wear blast furnace backup zones and reheat chambers. Silica refractories, containing over 95% silicon dioxide, exhibit an unusual property: exceptional creep resistance nearly up to their melting point. This makes silica the material of choice for high-temperature coke oven, batteries, and glass tank crowns that must not sag. Magnesia and Doloma materials dominate high-temperature basic steel processing due to their natural thermodynamic resistance to lime-rich slags. Basic oxygen furnaces, electric arc furnace slag lines, and ladle refining vessels rely heavily on magnesia-carbon formulations to prevent premature lining burnout. Silicon carbide bricks and nitride-bonded silicon carbide shapes excel in non-ferrous melting, blast furnace lower stacks, and waste incinerator chambers. These silicon carbide components resist abrasion, withstand severe thermal shock, and prevent molten metal wet-out. Furnace relining is a major mechanical overhaul executed under strict engineering protocols following a complete furnace shutdown. The vessel is isolated, locked out, and systematically cooled to ensure safe human entry. Localized erosion, deep gouging, or abnormal slag line wear provide valuable forensic data regarding furnace dynamics, burner alignment, and chemical imbalances. Once the steel shell is exposed, technicians verify structural tolerances, check for shell distortion, and replace welded metallic or ceramic anchors. Steel ladles receive custom-shaped magnesia-carbon bricks along the slag zone, with precision mortared joints to eliminate metal penetration paths. Monolithic linings rely on rigid steel formers positioned inside the vessel, with high-frequency external vibrators consolidating the fresh castable. The most critical step in monolithic relining is the initial dry-out and commissioning schedule. Chemically bound and free moisture must be vaporized slowly along a programmed, stepped temperature curve. Before any refractory leaves the production plant, it undergoes rigorous, destructive, and non-destructive laboratory testing. X-ray fluorescence and X-ray diffraction verify total elemental composition and confirm that target crystalline phases have formed properly. Refractoriness under load tests determine the exact temperature at which a standard refractory specimen softens and deforms under continuous mechanical stress. The permanent linear change test evaluates irreversible shrinkage or expansion after holding specimens at peak service temperatures for hours. A refractory lining may look like a simple wall of ceramic bricks, but it is a precision-engineered thermochemical defense system. Its success depends on careful raw material purification, tight particle sizing, controlled hydraulic pressing, precise firing, and disciplined installation. There is no universal refractory material capable of handling every industrial environment. The best refractory is the one precisely tailored to the specific chemical, thermal, and mechanical stresses of that exact zone. The next time you see molten metal, glass, or advanced ceramics processing in industry, remember the hidden refractory shields holding the process together.